I would like to present results of my latest research on the crash of the Polish governmental airplane Tupolev 154M in Russia that killed all 96 people on board, including the President of Poland, First Lady, 9 generals of the Polish army, among them 5 top NATO generals and the top civilian leadership of the country. Currently, I serve as an expert of the Polish Parliamentary Committee for the investigation of the Smolensk crash. In my presentation, first I will describe my academic credentials and expertise. Next, I will present the methodology I have used to analyze the airplane crash, and finally, the results of my simulations. I am a professor and chair of Civil Engineering Department in the University of Akron. I'm also editor-in-chief of the Journal of Aerospace Engineering. Other credentials you can see on this slide. At the bottom of the slide you can find 2 links which would lead you to all the information about myself and my research work. I would like to point out that together with representatives from Boeing, FAA, NASA and leading jet engine companies, I have been member of Aerospace Consortium for the last 15 years. The objective of this consortium is to develop a methodology and numerical tools capable to simulate dynamic experiments and high-energy impact events. This methodology was developed and tested in the aftermath of 2003 Shuttle Columbia disaster. Also, I had been working on this methodology with NASA to develop special braided composite materials and FE finite element models that could be used for a jet engine containment system. This braided composite material is already utilized by GEAE in their new jet engine called GEnx, which was selected by Boeing for Dreamliner Boeing 787. The similar types of braided composites materials were also selected by Williams and Honeywell for their new types of jet engines. To illustrate the high energy impact methodology, let me show you the impact experiment conducted using a gelatin projectile and braided composite plate. This is the same composite material which has been recently used for the jet engine containment system. To characterize this material, we had to conduct numerous experiments of that type. As part of this research, we also had to create a numerical model capable to simulate such impact experiments. Accurate numerical simulations can be called virtual experiments. First, we had to develop material models for gelatin and braided composites so we could simulate all kinds of impact experiments using LS-DYNA. You can see here deformation in 2 time instances. Each snapshot represents a comparison between real and virtual impact experiment. It is also important to predict the damage modes. In the case illustrated here, a butterfly damage shape agrees with the experiment for ±60 triaxial braided composite. Once the model properly represents the reality, we gain confidence that we can obtain deformations and failure shapes for any other similar material and for various structures. For example, if we change fiber architecture from 60 to 45 degrees in the composite, a different damage shape is produced. This shape can be correctly predicted using our model. The model so developed can be used by a jet engine company to design their proprietary engine components. The FAA requires that commercial jet engine manufacturers conduct at least one blade-out test in order to certify their new jet engine or any substantial modification of the existing jet engine. Such tests are very expensive. Let me show $20 million test as an example that was conducted in Rolls-Royce.
In this test, a small explosive charge is used to release a fan blade from the disc. The engine has to contain the fan blade safely and also has to contend successfully with the resulting out-of-balance forces. This is a technology in which Rolls-Royce has a clear lead over any other manufacturer. Nevertheless, the fan blade containment test is regarded as an essential demonstration of safety and integrity.
4, 3, 2, 1, quietly.
A released fan blade contains enough energy to throw a medium-sized car some 100 feet into the air. In a full engine test, this energy is absorbed as vibration through the engine carcass, truly one of the most impressive sights in aero engine testing. Without any apologies, we'll show that again. This is indeed one of those occasions when only seeing is believing.
Using the virtual test technique with developed material models, manufacturers can try different design concepts for their jet engine, virtually conduct blade-out test, and become more confident when the real test is conducted. You can see here the simulation of the blade-out test using the model that we have developed. As I said, the above shown braided composite material has been used for the containment system in GEnx jet engine, but also is considered by other aerospace companies for different applications. On the left in this picture you can see GEnx engine, and on the right you can see shaft of the helicopter engine. Before I show you how our methodology is used to analyze airplane crash, let me give you some background information about this particular crash. Russian investigating committee in their final report wrote in section 3169 that the aircraft collided with the verge with a trunk diameter between 30 to 40 centimeters, which led to the left outer wing portion of about 6.5 meters long ripped off an intensive left bank. Originally they put 4.7 meters, but then they crossed that and changed to 6.5 meters. It is worth to notice that the longer the portion of the wing is cut off, it cuts through a larger and stronger part of the structure of the wing. In section 3170, it says, in 5 to 6 more seconds, inverted aircraft collided with the ground and was destroyed. Let's take a look at the satellite picture on the top that shows the terrain between the verge and the crash site. The black line indicates the airplane trajectory. The white line indicates a correct path for landing. For yet unknown reason, Russian controllers directed this airplane about 50 meters away from the proper landing path. The plane was flying from the right to the left direction. The black lines shows that at the point of TAFs, the plane significantly and rapidly changed its direction. 1 second later, at the point indicated by FMS, the plane lost all electric power. Vertical trajectory shows that the airplane was climbing in accordance with pilot's command to go around. It means not to land, but something must have happened at 30-40 meters above the ground. The picture below shows the airplane trajectory according to the Russian report. It is marked as a red dashed line. The green vertical line indicates the location of the badge. The Russian report claims that the airplane hit this badge 6 meters above the ground. As a result, the badge ripped off 1/3 of the left wing of the plane, that is about 6.5 meters long fragment of the wing. The Russian trajectory suggests that after losing 1/3 of the wing, the plane is going down to about 1 to 2 meters. So at this point, the wheels and tail of the plane had to touch the ground because the pitch, which means nose, was 14 degrees up. From the verge to the visible road, the plane should shave all the vegetation, but there is no sign of any damage to the shrubs and trees on this path. Next, the Russians suggested that this 80-ton jet with 2/3 of the left wing jumped up with about 6G to 8G acceleration, then rapidly stopped climbing, and half a second later jumped again another 20 meters, again with 6G or 8Gs, in order to rotate and crash. Apparently, the airplane had to climb to that height in order to have enough clearance to rotate. The black trajectory line above the red has been developed based on the TAFS data obtained from the United Avionic Systems, Universal Avionic Systems, the producers of TAFS recorders. It was found and developed by Dr. Nowacek. According to this black trajectory obtained from TAFS, the airplane never hit the verge. In this slide you can see two pictures, one just after the crash of this airplane in April and the other in June. The official reports omit completely TAFS number 38 landing event, which is showing on both pictures. However, the examination of the geographic area corresponding with this event shows some special activities. This can be seen by comparing April 2010 satellite above to June 2010 below of the same area. In the second picture, all the trees in the area of TAFS 38 have been removed and grass has been burned out. Let's focus first on the impact of the wing hitting the birch tree. There are two objects that impacted each other, the birch tree and aluminum wing of the airplane. I'm not going to discuss particular material properties, but I will only mention that for the tree we use two different material models. First, one will be called generic, which is linear orthotropic, and the other one is special nonlinear model developed by Federal Highway Administration for trees, and it is called MAT 143. All the parameters are on this slide. I will also mention that for aluminum we will also use two models to build confidence about our results. But let's come back to the tree. It is worth to notice that wood is very sensitive to moisture content. In this plot you can see that wood loses 80% of its strength between dry conditions and 25% moisture content. In this plot you can see that the dry wood is very brittle and stiff, and wet is more flexible and compliant. Wood is also sensitive to the strain rate of loading, as shown in these two plots. MAT 143 model has all the above attributes. It was validated by Federal Highway Administration using special bogie, shown in the slide in the middle. The results of the validation is shown on the right side by using the LS-DYNA model. MAT 143 model was also used by a team of researchers led by Boccieri to simulate FAA experiment conducted in 1965 using airplane constellation. Mass of the airplane constellation is 40 tons, so about half of the Tupolev 154M. The initial velocity was 207 kilometers per hour, which is also about 70-80 kilometers per hour slower. At that speed, it sheared the landing gear, causing the aircraft to be airborne and quickly slide on its belly. The left wing struck an earthen barrier and the right wing struck two vertical telephone poles, as you can see in this short video. As I mentioned, airplane Constellation was much lighter and slower. The maximum speed of Constellation was 600 kilometers per hour, while Tupolev 154M was designed for 900 kilometers per hour. So the wing of the Constellation is much lighter, weaker than wing of the Tupolev 154M. You can see in this slide that Constellation wing has on the front and rear beams or spars along its length, and instead of ribs it has a series of trusses. The wing of Tupolev has additional inside beam and has series of ribs. In this slide you can see that the authors of the simulation of airplane Constellation validated completely their simulation with the experiment. They concluded that inboard pole is cut by the wing, inboard tank is compromised after impact with ground, outboard tank is damaged by impact with the second pole, and outward pole is also cut. Both poles fell in the direction of the airplane movement. So MAT 143 can be used for this type of crashworthiness analysis. Using the three-point bending experiment in my lab, we have also verified simulated behavior of the birchwood beam. And we found that generic material model is 4 times stronger than MAT 143. Please note that the force displacement curve produced by MAT 143 almost exactly covers the experimental curve, which is underneath of the MAT 143 curve. For the aluminum, we also use 2 material models. First, we use generic elastic plastic model and material properties obtained from the Russian database. And recently we use FAA developed nonlinear model called Johnson-Cook, which is strain rate dependent. These graphs illustrate stress strain produced using 2 material models for the birch on the left and 2 material models for the aluminum on the right. Next step is to develop a wing model for Tupolev 154M. This airplane was designed for 110 tons weight and 900 kilometers per hour speed. The internal structure of the 3 spars or beams and ribs are shown. Below you can see the cross sections of each spar or beam used in this airplane. I have not used stringers, so my model of the wing is weaker than the real one. You can see on the slide finite element method model of the wing internal structure. You can see 3 yellow beams and several green ribs. I can mention that we simulated impact for various plane configurations and various velocity vectors. The birch tree with the trunk diameter was selected to be 10% larger than reported by Russian, and you can see the birch density between 700 and 1000 kg per meter cube and other parameters used in our simulations. In order to use the aerodynamic pressures, we asked Dr. Brown from Mechanical Engineering Department to calculate those pressures using ANSYS CFX, which we added to LS-DYNA model. Let's see some of the results of our simulations. In this simulation, we can see the red airplane with green wing striking a yellow trunk of the birch. We can observe that the birch tree is cut within 0.02 of a second, and the airplane flies away with the speed 80 meters per second. The top part of the birch tree falls in the direction of the airplane movement, similar like in the simulation of the airplane constellation. Here you can see that the trunk of the birch causes damage to the front edge of the wing, but the birch is cut by the first beam inside of the wing, exactly the same way as it was done in the simulation of the plane constellation, confirmed by the experiment. This simulation illustrates the generic material model application. Even using very fine mesh, as it is shown in this slide, and utilizing more accurate nonlinear material models, which is MAT 143 for the birch and Johnson-Cook for aluminum, we always obtain similar final results. It means the birch causes damage to the front edge of the wing, the birch tree is cut by the front beam of the wing, the lifting surface of the wing is not damaged, and the upper part of the birch tree falls down in the direction of the airplane movement. Here we can visualize the same case from the bottom point of view. The lower part of the tree is pushed forward and due to its inertia cannot stop before the airplane flies away, even if the plane flies horizontally with the pitch 14 degrees. So the bottom side of the wing is not damaged at all. In this case, the plane has 79 meters per second horizontal velocity vector and 19.7 meters per second vertical velocity vector. Again, the front edge of the wing, about 60 to 80 centimeters in length, is damaged. The birch is cut to two pieces and the airplane flies away. In all cases, the top part of the birch always lands parallel to the direction of the airplane movement. It is worth to note that photographs of the real birch tree from the Russian report shows that the upper part of the birch tree landed perpendicular to the direction of the airplane movement. So we can conclude that using parameters provided in the official Russian and Polish reports, the LS-Dyna finite element method model shows that the wing of the Tupolev 154M plane cuts through the birch for every analyzed scenario, for all original and nonlinear rate-dependent material models, for the finest mesh. The damage to the wing is localized on the edge, does not deteriorate the lift surface of the wing, thus should not significantly reduce the ability of the plane to fly. Above simulations have been positively evaluated by Boeing principal structural engineer Dr. Wacław Berczyński. The photograph shown in this slide was put together by Mr. Marek Dąbrowski. You can see here that the front edge of the wing, of the left wing, in the potential area of contact with the birch was not destroyed. Instead, the internal part of the wing behind the edge has a big hole. If we go to this slide and see, we can see the reconstruction of the left wing from the bottom, and we can conclude that there is no visible damage of the wing edge. Real tree lays perpendicular to the airplane flight direction, and there is an extensive internal wing damage, including ripped off rivets, and all of that suggests that there was no impact between the birch tree and the left wing, and an explosion near the point of tufts could explain the damage of the wing and a rapid turn left of the airplane. Let's go to the next part of the crash analysis. Now I am going to investigate the fuselage damage if it is dropped vertically to the ground at the inverted position. In this simulation of the inverted fuselage, we can see that the walls and the ceiling are crushed under the red floor of the airplane. Same can be observed even if we add angular velocity to the drop velocity of the segment of the fuselage. Sandia National Lab conducted similar studies, but using the effect of the explosion inside of the fuselage. I can show now one of many simulations conducted by Sandia National Lab.
That information is being used to create a computer model which shows not only how a plane is built, but how it will behave. Pressure data from different explosive tests are added.
Homemade liquid explosives, homemade powdered explosives, gels, just about anything that the terrorists might consider.
The model is helping scientists determine what damage different explosives will do, placed differently in different aircraft at different altitudes, what it will take to bring a plane out of the sky.
So, if an explosion happened in the fuselage before the plane crashed into the ground, in the inverted position, the walls and the ceiling of the fuselage can open outside before the crash, and they will not be crushed under the floor. This is exactly how the section of the fuselage of Tupolev 154M was found in Smolensk crash scene. It is shown in this photograph. You can see the right wall, and then the bottom of the fuselage with the floor. On the other side is left wall, and completely outside the ceiling or top of the fuselage. Sandia National Lab simulation results explain this configuration by explosion in the air before the crash. I conducted now the simulation with the explosive using LS-DYNA. We can see that both walls and the ceiling open outside before touching the ground. So neither side of the wall or ceiling is crushed under the floor. This photo is taken from the presentation delivered by Professor Dr. Jan Obremski, entitled Description of the Method of Destruction of a Small Fragment from the Tupolev 154M airplane, that was presented at Smolensk conference in Warsaw, Poland on October 21, 2012. You can see the size of a small fragment. Some of the fragments are even smaller than that. You can see here the ripped off rivets, and according to analysis of Professor Dr. Jan Obremski, this part has typical signs of explosion from inside out. Finally, let's assume that there was no explosion, and let's analyze what would happen if Tupolev 154M airplane as an intact structure crashes into the soft soil in Smolensk. The soil model was developed using Federal Highway Administration direction, and that model is called MAT 147. You can see on the screen the experimental system to develop the shear behavior of the soil. On the right top is 2 experimental data, and on the right bottom LS-DYNA model used for characterization of this MAT 147. We have considered 2 configurations for the airplane crashing into the ground, for 30 degrees striking angle and for 10 degrees striking angle. Both cases are analyzed in the regular and inverted positions. For the 30 degrees crash, the vertical velocity is about 40 meters per second, which is more than 5 times faster than any probable velocity of Tupolev 154M, considering that this plane dropped from 30 to 40 meters. The simulation shows deep and elongated crater formed in the soil. If the airplane crashes at the angle of 10 degrees, the vertical velocity is 14 meters per second. And craters are not as deep, but they are longer and clearly visible. So we can conclude that large and deep craters should be visible if the entire mass of the airplane was intact at the moment of crash. No crater detected at the scene, but large field of debris suggests that the airplane disintegrated in the air.
This 727 is about to crash.
In this slide we can see the disintegration of our airplane model due to impact with the soft soil. The plane breaks into 3 pieces. Most of the damage is concentrated in the front part of the airplane. TV Discovery has shown recently an experiment conducted this year in Mexico, where Boeing 727 was crashed into the desert soil. Tupolev 154M is very close copy of Boeing 727. In this experiment, the plane, you can see the video of this crash. The simulation of the same airplane crashing in the inverted position produces even less destruction to the fuselage than the simulation for the crash in the regular position. Accelerations felt by passengers are even smaller than in the regular crash situation. This is one of many examples of real crash in the inverted position. Dr. Witakowski mentioned that about 4% of all crashes are belly up. In this case, the Tupolev 134 crash landed upside down in Kyrgyzstan. All passengers survived and 31 was injured. In this example, Tupolev 154 crashed into the forest, broke into several pieces but did not explode. The report says that all people survived, 83 were injured. I heard that 2 of the passengers died later on, perhaps in the hospital. In the case of Polish Tupolev 154M, all passengers died. The airplane disintegrated into millions of pieces as small as a hand over the large area of about 2 square kilometers. Some parts of the fuselage were found in a regular position, some parts were found in the inverted position. Rivets were found in the bodies of some passengers. In the fall of 2012, some Polish experts sent by the Office of Prosecutor were allowed to investigate the wreckage of the plane and the crash scene in Smolensk. Using electronic detectors, they have found with 99% accuracy, traces of explosives on the inside and outside parts of the airplane. They collected several hundred samples for the lab tests to confirm their detection, but the Russian authorities did not allow them to take those samples to Poland for testing. We hope that those samples will land in Poland soon. Final conclusions. Separation of 1/3 of the left wing could not be caused by the impact with the birch tree. Most probably, separation of a fragment of the left wing was caused by explosion in the air. Open walls outside of the fuselage indicate mid-air explosion. The unprecedented degree of damage and the large number of shrapnel indicate high-energy mid-air explosion. Lack of a visible crater at the crash scene indicate that the airplane disintegrated in the mid-air. Without a mid-air explosion, most of the passengers in the center and aft sections of the airplane should survive any crash from 30 to 40 meters into the soft soil. Official Russian report attributed death of the passengers to 100 G acceleration. Such acceleration could be explained by explosion in the fuselage, shockwave produced by explosion, and or a direct impact of the passengers with the ground at 80 meters per second without any protection of the fuselage. Thank you.